So the next question is, how do these calculated standard deviations spread in further calculations, or how do they affect calculations or computations that are done using a couple of standard deviations? For example, let's say that there's a rectangular piece of land, and this is measured with a adjusted value of 5 feet plus minus 0.5 inches, and this side is measured 6 feet plus minus 0.6 inches. So then what is the area and what is the standard deviation of the area? Calculating the standard deviation of the area falls under the term error propagation. However, this is an incorrect term. So this is an incorrect term because it's not the error that's spreading, it's the standard deviation that's actually spreading. So the error is always with respect to the errorless value, and that's why it's an incorrect term, but that's what's being used. So we'll just call it error propagation, and there's one simple formula for error propagation. That is this sigma out. That's the covariance variance matrix of the output is equal to the Jacobian times the sigma input times the Jacobian transpose. And this is a different Jacobian than the least squares adjustment Jacobian. The least squares Jacobian is with respect to the unknown. This J is with respect to the known values. So how does the sigma input look for this? So the sigma input for our example would be, let's call this side A, let's call this side B. Sigma A squared 0, 0, let's say there's no covariance between the measured values. And it doesn't matter what order they're in, as long as the order is going to be consistent further on. So this is all. So this is how the sigma input would look like. And what's the Jacobian? Well, for the Jacobian, we have to write down our equation that calculates the area, and that's A times B. That's implying that these are all the right angles. And since our first term is first term in our covariance variance matrix, where our first index is sigma A, so our first partial derivative is going to be with respect to A, and with respect to B. So the partial with respect to A is just B. The partial with respect to B is just A. So sigma out is going to be B and A. So that's 5, the measured value, not the standard deviation. The standard deviation comes into play in the covariance variance matrix. And 6. Then we have to make sure that the unit of measurement is the same everywhere. So 0.5 inches equals 0.5 over 12 feet. 0.6 inches is 0.6 over 12 feet. So make sure to use the same standard deviation. So sigma A is 0.6. That's 0.6 over 12 squared, 0, 0, and 0.5 over 12 squared, 5, and 6, which is going to be the Jacobian transpose. So then we can put that into our Octave or MATLAB. So my J is 5.6. And blocky bracket. And I'll call my big sigma, it's this E, this kind of looks like a sigma, En. Oops, equals 0.6 over 12, 0.5 over 12. Oh. Squared, 0, so that's good then. Equal Jacobian transpose That's the apostrophe. So that's our E out. However, this can be considered a 1-by-1 matrix. And remember that the diagonals are always the squares of the standard deviation. So sigma of A of the area is going to be equal to the square root of E out, or 0.35. It's about 0.35. Square feet squared, or feet squared. And the area is going to be A times B, so that's 30 square feet, plus or minus 0.35 square feet. So in a covariance variance matrix, the diagonals are always going to be the standard deviation squared, or the variances. That's why it's called the covariance variance matrix. And the off diagonals are going to be the covariances. So here's a nice example. Suppose we measure a volume of a cylinder, which is pi r squared L. So L is the height, R is the radius, so V equal pi r squared times L. Let R be 1 centimeter and L is 1 plus 0.5 centimeter. And error propagation should give us pi over 2 cube centimeter squared standard deviation. So this is exact, and there's probably going to be a problem because the standard deviation is 1/2 of the actual measurement, so that's not a good sign. So sigma out equals Jacobian times sigma input times Jacobian transpose. We've got our equation, so that's already given to us. We have two known values, r squared and L. Well, r and L. Pi is a known value, but that's a constant. That's going to be constant for any r and L values. So our sigma input is going to be sigma squared, it doesn't matter what order, sigma squared R, sigma squared L. And then the Jacobian has to be in the same order. The first one was with respect to R, so this is partial with respect to R, partial with respect to L. Partial with respect to R is 2RL. And partial with or 2RL pi. And then pi r squared. So the Jacobian is 2 times 1 times 1 times pi, and pi times 1 squared, which is 1. So it's 2 pi and pi. So this is going to be sigma r is 0, 0, 0. It's already in centimeters, so it's 1/2 squared. So sigma out is going to be equal to 2 pi pi 0, 0, 0, 1/4, and 2 pi and pi. So this times this is just going to be 0. 2 pi times 0 plus pi times 0. 2 pi times 0 is 0, and that's pi over 4 times 2 pi. Zero times 2 pi is 0, and that's pi squared over 4. And that's our sigma out. So sigma v, is going to be the square root of sigma out, or basically pi over 2. And what's the volume? R is 1, so that's basically pi plus minus pi over 2 and centimeter. So these are both in centimeter cubed. So the uncertainty is actually 1/2 the actual volume, which doesn't bode well. That is, with the within the 2 sigma range, the volume can actually be 0. If 1 sigma is pi over 2, 2 sigma is pi. So the volume, so the volume can actually be 0. And this is the similar problem as before. And before we go into this one, let's take a look at what happens if we switch R and L. If we switch R and L, so this is going to be L, this is going to be R. So then this would have to change to L, and this would have to change to R. So everything's going to be flipped, and everything's going to be flipped over here. But the result is going to be exactly the same, because since everything flipped over here and everything else flipped over here too. In that case, this is going to be pi r squared and 2rl pi, pi and 2 pi, and then this would be 1/2 squared and 0. So this would be pi and 2 pi, 1/4 0, pi and 2 pi. So we'd still get pi over 4, 0, pi and 2 pi, and we'd still get pi over 4, or pi squared over 4, because this times this would still be 0, so it works out the same way. So let's take a look at the next example. And over here we have a leveling example with a benchmark. Benchmark is given of 20 meters, and there's a difference of 5 meters between HA and H1, and a difference of -8 meters between H1 and H2. And we're given the covariance variance matrix right here in millimeters, well, millimeters squared. So the standard deviations are given over here. This is for delta H1, this is for delta H2. And the question is, what is H1 and H2, and what are their standard deviations? So let's draw that up. So this is HA equals 20 meters. To H1. And -8 meters to H2. And we're given sigma or C for 9. So from this we know that delta H1 is the square root of 4 millimeters squared, or 2 millimeter, square root of 9 millimeters squared, or 3 millimeters. So this is plus or minus. And the question is, what is H1 and H2 and sigma big H1 and sigma big H2? So H1 is fairly easy to calculate. It's HA plus delta H1 so it's equal to 25 meters, and H2 equals HA plus delta H1 plus delta H2. So that's 5 minus 8 is minus 3, so it's 17 meters. So the calculation of sigma H1, and our basic equation is sigma out equal Jacobian times sigma input times Jacobian transpose. So this is going to be our sigma input. And since the off diagonals are 0, that means there's no covariance or correlation between the measurements. So the Jacobian, take the Jacobian with respect to the known values. So we have our two equations. Partial of delta H1, or the partial with respect to delta H1 and delta H2. It's just 1, and there's no H2 over here, delta H2, so it's 0, and 1 and 1. So sigma out equals 1, 0, 1, 1, 4, 0, 0, 9, and Jacobian transpose. So this times this is 4. Zero, 9. So this is 4. And 13. Four, 4, 4, 13. So it matches up, although it did it slightly differently. And that's fine as long as it's consistent. Since this is a negative value, this can also be represented with a -1. But as long as the setup is consistent, it's going to work out. So what does this mean? The solution is going to be in the same order as the Jacobian. So from this, let's see, where should we? So this is the sigma out. So the diagonals are going to be the variances in the same order. So sigma delta H1 is going to be the first term. Or well, sigma squared H1 is going to be equal to 4 millimeters squared and sigma delta H2, or not delta H1, I'm sorry. So this is actually H1, big H1. Sigma big H2, or sigma squared big H2, is equal to 13 millimeters squared. and the off diagonals are the covariances. So since H1 is the first one, H2 is the second one, it's going to be in the same order. So sigma H1, H2, the covariance is going to be 4, and the covariance variance matrix is always a square symmetric matrix, which it is in this case. So how do we calculate the correlation between H1 and H2? It's the covariance divided by the individual standard deviations. And it's around 0.6, so that's pretty high.